Alright, in this video we'll be going through the 2017 Wave Systems exam. Starting off course from the beginning. Right, so we have a clarinet, bunch of information, investigating the Doppler effect, and it asks us in A, on the diagram below, draw the first harmonic and label the nodes and antinodes. Now the first harmonic for a closed pipe looks a little something like this, where we have air going back and forth through here. So we have an antinode there, we have movement, and on our end here we have a node because air cannot move about that end. It can't move beyond it, so we have a fixed point, we have a node. All right. The clarinet produces the fundamental frequency and several harmonics. Explain why the clarinet does not produce any even harmonics. Now, if you remember about closed pipes, they don't produce even harmonics, as the question suggests. And the reason for that is we have an antinode at one end, so we must have an antinode and node at each end. Okay, and that requirement means that we cannot have multiples of half wave harmonics. So we cannot have so one way to think about that is if I say draw a wave, right? So we have a wave. Well, if you look at our above diagram here, we have an antinode, so we have movement, and then we have a node, no movement, right? So at the peak here, that's what I'm calling an antinode, we have movement, and at the bottom here we have a node, no movement. Okay, that's a quarter of a wave. Say if we were to have a half wave, say if we're going to say here, well, no, we can't have that because we'd need a node on one end and a node on the other. We can't have that with a closed pipe. We need an antinode on one end and a node on the other. Same thing if you thought about having, say, if we move over here, that's allowed. That's fine because we have a node at one end and we have an antinode at the other end. Shift over a bit more. We can't have that because we're going to have two nodes at each end. So the only allowed configuration, say if we had a closed end here, we could only have one there, we could have another one there, and another one there, and so on. But you'll note that we can't have half multiples of the wavelength. Continuing on. Right, when the train was approaching Ballet at a speed of 5 meters per second, he heard a frequency of 139 hertz from the clarinet, showing that the frequency of the sound heard by the clarinet player would have been 137 hertz. Let's break down the values that we're given. So, we know that the velocity of the source, so our train, is 5 meters per second. We know that the frequency heard, so F prime, our frequency changed, is 139 hertz. Now, we know the velocity of the wave, because if you might remember, if we scroll up here, it tells us that the speed of the wave is 341 meters per second. So let's put that in. So our V wave is 341 meters per second. Okay. So if you cast your eyes to your formula sheet, you will find the formula that our changed frequency, our F prime, is equal to our original frequency, which we're showing that it's 137 hertz, multiplied by the velocity of our wave, divided by the velocity of our wave, plus or minus the velocity of the source. Now, in this case, because the train is approaching, we're told that it is approaching, that means that is a minus sign. There are several ways to remember it, but honestly, just remember that it's a minus if it's coming towards and it's a plus going away. Not that difficult. Now, we are trying to find just our normal f here, which means we need to solve this equation. To solve that for f, we can just do that all in one. I'm going to divide both sides by our VW, so I get F prime divided by VW, and I'm going to multiply both sides by VW minus VS, so I get VW minus VS. Okay, we're ready to throw in our values. So our F prime is 139 Hertz, and our VW minus VS, well, we can just do that all in one. So we know that our VW is 341. If we take away 5 from that, we get 336. So I'm just going to times that by 336. And we'll divide that by our V wave, which is 341. And calculating that, I find that to be 136.9619. And if we're going to round that, that goes nicely to 137 Hertz. And bloody good thing that is, because that's exactly what we're looking for. Moving on to the next question. A second clarinet player was standing beside Ballot as the train approached. She produced the same frequency as the clarinet player on the train, causing Ballot to hear beats. So Ballot is sitting there. She's getting one frequency, so our frequency 1 at 137 Hertz, and another frequency of 139 from the clarinet player on the train. Frequency 2 is 139. So one clarinet is right next to her, standing still and giving a frequency of 137, and the other is on the train, Doppler shifted, so we get that as 139 Hertz. Okay, now the beat frequency is the difference between those two, so our frequency of our beats is going to be just the difference, which is 2 Hertz. And our question asks, okay, explain why the sound reaching Ballot from the clarinet on the train did not have a frequency of 137, and explain why beats are heard, and calculate the beat frequency. Well, we've already done that. So, the train sound was Doppler shifted from 137 Hertz to 139. When two frequencies are played, they alternate between constructive and destructive interference. Constructively and destructively interfering, we'll say. This creates an oscillation in amplitude we refer to as beats. Okay. Moving on. That handwriting is disastrous. Okay, question 2. Mike and Kate are on a tramping trip and are crossing a bridge. They're jumping up and down, standing waves. The bridge is 2.4 meters long. Okay. Describe one difference between a standing wave and a traveling wave. Well, standing waves are stationary. Or rather, standing waves don't propagate. Traveling waves do. Okay. A bridge can oscillate at many harmonics. Show that the frequency of the third harmonic model is, well, 3 times velocity divided by 2L. Okay. So, our third harmonic is going to look a little bit like this. So we have our 2 fixed points there. Oh, up. Yep. Okay. So, our wavelength for the third harmonic here is, you can see that we have our full wavelength is here between these 2 points, and that distance there, our wavelength, is 2/3 of the total length. Okay, I can never remember these, so I just draw them out in order to remember. So knowing that, we also know, so we have that equation, we also know that the velocity of the wave is equal to frequency times lambda. That is included on your formula sheet. If we solve that for our lambda, our wavelength, we get that our wavelength is equal to the velocity divided by the frequency. Now, if we substitute V over F for our lambda here, well, let's see what we get. We get our V over F. V over F is equal to 2L over 3. Now, if we massage that around a bit, if we flip both sides, so if we get that, we have our F over V, we can do that over 2L. Okay, multiply both sides by the velocity, and we end up with 3V over 2L. And it's a damn good thing that is, because that's exactly what we're looking for. Okay. The bridge oscillates at the fundamental frequency mode with a period of 1.8 seconds. Calculate the speed of the waves in the bridge. Okay, so we know that our period is 1.8 seconds. Okay, now we're looking at the fundamental frequency, which looks like this. Okay, so that there is half a wavelength, which means that our wavelength is equal to 2L. Okay, and we're given L. L is, well, I can't remember, but I do remember we were given it, 24 meters long. Okay, 24 meters. Now, we want to find the speed of the wave. So, if we have our frequency, this is an equation you're given, is equal to 1 divided by 1.8 seconds, our period, right? And if our lambda is double that, we know that our wavelength, 2L, is going to be equal to 48 meters. Now, going back to the equation right here, we can use that again, knowing that the velocity is equal to the frequency times wavelength. We know that that is going to be our 1 divided by 1.8, and times that by our wavelength, which is 48. And calculating that, I get a value of 26.6667, which we will round to 26.7. And don't forget your units, meters per second. Okay, Mike is 6 meters from one end and Kate is 6 meters from the other. Give a comprehensive explanation of how it is possible for Mike and Kate to cause the bridge to oscillate in the second harmonic. And you should include a bunch of things in your description. Draw a labeled diagram of the bridge oscillating in the second harmonic mode. Okay, well, let's do the diagram first. So we have our ends here. Okay, I have a node in the middle. So our wave will look something like that. Okay. Mike is 6 meters from one end and Kate is 6 meters from the other. Right, so that means that our Mike and our Kate, they must be on this here, on antinodes each. So they are both creating these antinodes. They are pushing that bridge up and down to create this pattern. And of course, we have a node right there in the middle. So Mike and Kate are creating the two antinodal points. By jumping at those points. All right, and explain the phase relationship between their oscillations. Okay, the antinodes are 180 degrees out of phase. Now we know this. Looking at that diagram, we can see that these two antinodes are 180 degrees out of phase. What that physically means is that as one has gone up, the other has gone down. Okay? What else are we wanting to say? So we've got their phase relationship between their oscillations. Yep, drawn the labeled diagram. We've explained their positions. They are antinodal positions, which makes sense if we have a total distance of 24 meters. We have our 6 meters from the ends. Which means that we'll, of course, have our 12 in the middle. So everything's adding up and everything's accounted for. Now, it's always worthwhile, and they've basically asked us to do this, explain exactly how a standing wave is created. So, standing waves are created when waves travel past each other. This creates a series of nodes and antinodes, or destructive and constructive interference, respectively. Okay. All right, now for question 3. So, we have a diffraction grating set up, as we can see in the picture. The slits in the diffraction grating are 2 times 10 to the minus 6 meters apart, so let's actually write that down. We have the angle between the central antinodal line and the first antinodal line is 15. So for n equals 1, we know that our angle is 15.4 degrees. And we are asked to find the wavelength. Now, the equation you are given on your formula sheet is that d sine of your angle is equal to n lambda, which means that d sine theta divided by n is equal to your wavelength. Now, if we put in our numbers, we get 5.31111, okay, and we'll round that to 5.31 times 10 to the minus 7 times 10 to the minus 7 meters. Don't forget your units, and that is fortunate because that's exactly what we're asked for. Okay, explain what causes the bright spot at the first antinode. All right, this is a big question. So at first antinode, our waves are all meeting in phase. We'll say roughly in phase. This creates constructive interference. Along a region known as an antinodal line. Just to expand on that, this means that peaks are meeting peaks and troughs meet troughs. Okay. Moving on, the picture at the top of page 7 shows the pattern she sees using the green laser. She repeats it using the red laser, which is a lower frequency, and we are asked to draw a pattern of what she would expect to see with the red laser and explain why the pattern is different to the green laser? Well, for this occasion, we can bust out our red marker here. So, red diffracts more than green, okay, because it is of a lower frequency and a longer wavelength, which means that our dots are going to be more spread out. Okay, we'll just go around there, and we should just make that clear that that is the central brightest antinode there. So let's explain that. Red has a longer wavelength. This makes it diffract more. Than green. Thus, the pattern is more spread out. I think we've answered it. Okay. Let's move on to D. So we have white light being shone through a diffraction grating, and there are 3 complete spectra produced. Now, we have the frequency of violet light and the frequency of red light, and we're asked to calculate the minimum slit separation. Well, let's draw exactly what's going on. So say we have our diffraction grating there, we have our light source, and say we have our screen. So we have our central n equals 0 line there. We have our 1, 2, 3, our 1, 2, 3 order numbers, and it is symmetrical on the other side, but hell, we might as well draw that. 2, 3, 1, 2, 3. Now, each of these order lines has a complete spectrum from red to violet. Now, the color that is going to be the most diffracted, have the greatest angle for each of these lines, is going to be the red. So our red for our first order, is going to be to this side there. For our second order, it's going to be diffracted a bit more than the violet. And for our third order, once again, it will have the most diffraction. So we want to know that if we have this red line at the greatest angle it could be, and that greatest angle, that maximum angle, is going to be 90 degrees. Okay, you can't go any further than 90 degrees. This angle here can't be any greater than 90 degrees. Otherwise, you are reflecting back, which we can't do in this case. And we're asked, in this case, what will our slit separation be for our frequency of our red light, which is the one that's diffracting the most. That's why we're using it, which is there. And, well, might as well write that. Our frequency in this case is our 4.3 times 10 to the 14. And always put your units, that is in hertz. Okay. Now, we also know that our n is equal to 3. So that's helpful. N is equal to 3. And our equation on our formula sheet that relates to this is that d sine of our angle, theta, is equal to n lambda, where we are trying to solve for d. Solving for d, we divide both sides by sine theta, and we get that our slit separation d is equal to n lambda divided by sine of our angle. Now, you might notice that we don't have lambda, but we do have frequency. So another formula you'll be given on your sheet is that the velocity of the wave is equal to the frequency times the wavelength. Thus, our wavelength is equal to our velocity divided by our frequency, where our velocity is the speed of light, because we are dealing with light. So that means it is 3 times 10 to the power of 8 meters per second. Okay. Substituting that into our equation here, we get NV divided by our lambda sine of our angle. Okay. Putting our numbers in, we get 3 on top. I have made a mistake. That should be, let's rub that out, that should be frequency, not lambda. Frequency. And let's calculate that. And I get 2.09 times 10 to the minus 6, which will round to 2.09 times 10 to the minus 6 meters. There we go.